welcome everybody to Speakeasy JS. I'm Faraz, and I will just quickly introduce what Speakeasy JS is all about. So this is the meetup for mad science, hacking, and experiments. So mad science is all about pursuing your interests and doing things for no other reason than just because you can and because you feel like it oftentimes. So it's about following your curiosity and building things that some people might argue shouldn't actually be built or that they don't think can be built. But oftentimes it's just fun to build things like that people don't think that can be done. And that's actually what our speaker today is going to be talking about. So today we're joined by Elena. And Elena is going to be talking about Ironfish, which is a novel cryptocurrency focused on privacy and accessibility. Before we get into it, though, I'm just going to introduce the other panelists and the speaker here. So everybody say hello.
Hi.
Cool. And so Elena is going to be sharing all about how they fit an entire blockchain full node into a web browser, which just to me sounds like it's going to be crazy. There's going to be some craziness involved in doing that. So I can't wait to hear all about it. So Elena, I think without further ado, I'll just let you take it away.
Cool. Yeah, thank you for the introduction. Yeah, so before I get started, I kind of want to give like a brief history about who we are and what blockchain is, like what we're trying to do and like how we even got here. And the brief history is that we started in 2018, early 2019. And we wanted to build an easy-to-use, privacy-focused cryptocurrency. So I don't know how many people here like are familiar with blockchain and what that means, or what zero-knowledge proofs mean. I'm happy to go into that. But I can also go into like how we built it outside of blockchain too. But my biggest point here is that we actually started all in Rust, and we started everything in Rust primarily because the open source cryptography libraries that we wanted to use were all in Rust, and so it was kind of a natural transaction there.
Elena, maybe you could. Sorry to interrupt. I just was wondering, maybe you could tell us a little bit about just like what the vision for Ironfish is. Like, what does an end user see when they use it?
Oh yeah. So right now, if people are familiar with blockchain, for instance, so for Bitcoin or Ethereum, they're like the way they work is because it's so transparent. Like if I wanted to send like you for us, for instance, like 1 Bitcoin, the reason why that would work is because all the verifiers know that my wallet has at least 1 Bitcoin, and therefore I can send your wallet at least 1 Bitcoin. So it works because of transparency, which is great. But like if you're thinking about it, okay, like well, actually, if I really want to build like a financial like instrument here, I don't want everyone to know how much is in my wallet. I don't want everyone to see every transaction that I've ever made, permanently stored in this like decentralized public ledger. So how do we make it so that the verification mechanism is like a bit different here? So it's actually not about like what I want users to see. It's actually what I want them to not see. So whenever you make an Ironfish transaction, it's public in the sense that anyone can join, anyone with a laptop or an iPhone or like any device that connects to the internet can participate in the Ironfish network and can make a transaction. But when that transaction actually gets posted, it doesn't show any of that information. So it actually hides who the sender is, who the receiver, and the amount. And instead, the verification mechanism is actually replaced with something called a zero-knowledge proof. And a zero-knowledge proof is basically this like really novel cryptography that allows you to prove something about hidden data. So I can prove to you, for instance, that my wallet has a certain amount without actually showing you my wallet, without actually showing you the contents of my wallet. So now I can make like an encrypted transaction and send it to Faraz, such that Faraz's wallet can decrypt it and actually see that transaction. And all the verifiers can still verify that transaction using that zero-knowledge proof, but they don't necessarily have to see who I am or who Faraz is or any other things about that transaction other than it's valid. So does that answer your question?
Yeah, totally. Yeah, it's great.
Cool. Yeah, so a lot of this is like already built in Rust. In fact, like even like cryptography outside of the blockchain world is all kind of moving into the Rust world. And for those people who aren't familiar, Rust is like a very strict, strong typed language. The compiler will do its best to make sure that you don't mess up. And it's on one hand, it's a hard language to work with because all of a sudden like with other languages like Java or JavaScript, it has like garbage collection and like memory management for you. In Rust, you are the garbage collector, and you have to manage your own memory. So you have to be like very cognizant of like, okay, like when I make an object, like how do I pass it, like who owns what, which makes it extremely safe, and that's why like the cryptography world is moving into Rust. But it does make it fairly annoying to work with, and I'm sure like people who have worked with Rust, they like. I feel like everyone secretly who works with Rust has like a love-hate relationship, because there's certain things where you're like super amazed about the language and like how thoughtful they were, and then there's some other things where like, okay, wow, like if I had written this in Python or JavaScript, I would have literally been done, like weeks ago. So it is definitely a double-edged sword, and that's kind of my next slide. Like this was like developing Rust was a lot of this. So compile times were very long, development cycles were very long. From the open source community, it's kind of like in this like middle mature state, so it's not quite mature yet. So if you want to find some open source library, the chances are you might find it, but maybe it's like not super developed or maintained. And so it's kind of like this kind of mid to early ecosystem still, in my opinion. So, and the thing that I really want to focus on is the networking part. The networking part was hard. So we personally took a dependency on something called Rust libbtp, and Rust libbtp is the Rust version of the libbtp project. And the libbtp project is actually this massive project from a company called Protocol Labs. They made a project called IPFS, if people are familiar with that. So IPFS actually uses a libbtp. And Filecoin is the thing that just launched, huge project. They also use libbtp. So it's actually like as a project, it's like very beefy, very mature. The Rust version, however, isn't so mature, and that's like what we had to work with. And it was actually like very, very hard to work with. And part of the reason is Rust is written in this very generic way. It was meant to support multiple transport layers. It started with TCP, but like the idea is that you could use anything. You could use like UDP, Bluetooth, like satellite. You can do anything you could possibly want to kind of have your networking layer. But in practice, it was actually like very, very difficult to work with. And most importantly, it didn't have NAT traversal. So we actually kind of looked at it, and we actually got like really annoyed with Rust libbtp, and we decided to build our own. And so we had zero experience in networking, so we didn't realize how hard this was going to be. But we looked at Bitcoin's networking code, and we thought, wow, this seems so simple. Like, why can't we just do it ourselves? Now, for the record, the Bitcoin networking code is actually very simple, and it's simple because it doesn't do NAT traversal. It actually doesn't do any encryption. So it's actually like plain text on the network. So it's actually like the most simple way of how you can do like networking code is like the Bitcoin library. And so we looked at that and we're like, okay, great, we can just build our own. So then like we started looking more into like, what does that even mean? We like researched more like, what is TCP, what is UDP, what is QUIC? And we quickly realized that there's this kind of problem that I personally actually was not aware of until we like did more research on this, which was this thing called the NAT traversal problem. And for those people who don't know of what that is, the concept is pretty simple. So, you're probably in a laptop right now, and you probably have a router. And so your computer can like request data. So if you go to like facebook.com, for instance, it goes to your router, the router like makes the request. But for instance, because of that router, it's actually very difficult for a device outside of the NAT to like communicate directly to the device behind the NAT, because that public IP actually isn't revealed. And so for like peer-to-peer networks, there's actually a problem that almost everyone has to deal with at some point, or to some degree. And if you want to learn more about it, libbtp actually has a great doc kind of explaining the NAT traversal problem and kind of ways around it. So there are a ton of ways to get around it. And there's something called like hole punching. So you're trying to figure out, okay, like how do I get around the router and actually get like that device's IP? And there's a method to do that called the stun. There's AutoNAT, when like your router actually like matches the same like internal IP port to your external one, so you can like guess what that IP is. There's something called turn, which is kind of like the middleman that kind of facilitates connections for you. And so when we kind of looked into this, we're like, okay, this is actually a lot of work. And then what we realized is that what we want to build is actually already built, and it's called WebRTC. And WebRTC, I mean, if you guys know Frost, I'm sure you know what WebRTC is. It was actually built for like peer-to-peer video streaming first. And actually does a lot of those things kind of for you. So you kind of like get all that effort for free, almost for free, if you use WebRTC. So then we actually had to make this huge decision of like, do we stick with Rust? And the reason for that is we didn't actually find any WebRTC implementations that we were super happy with. And truthfully, none of us were super eager to continue working with Rust. And then we kind of had this like philosophical question moment of what was Rust actually gaining us? Like, what was it giving us? And our two biggest bottlenecks were I/O. So we had to read right from the database quite a bit. And then it was the network side, it was bandwidth. And so even though Rust as a language is like very performant, very fast, for the large part, it actually like wasn't really helping us because the bottlenecks were somewhere else. And then we realized, okay, actually, if we have our networking stack in the web browser, or like to be web browser compatible, can we actually fit all of our other layers to be in the browser too? And for those people who are like familiar with like blockchains, like if you think of like the Bitcoin full node, you have to download this client, and I feel like I should have added a snapshot of what that client looks like, because it looks like it was developed in the 90s and probably like never updated. And it's like you have to install a desktop app. It starts syncing. It syncs for hours, and that's actually the fast mode. For Ethereum, it takes days. So it's like traditionally when you think of a full node for a blockchain, it's like this super hefty thing that like only like the super tech people can like understand like what that even means. The UI is pretty bad, and it's usually like requires a ton of resources from your computer. So we embarked on kind of a building an Ironfish node that works both as a CLI implementation, and I'll kind of go over why we actually kind of need that, as well as this web implementation that works entirely in the browser. So a brief kind of overview of what a blockchain is. So if you have heard of any other blockchains, there's Bitcoin, Ethereum are obviously the biggest two. But if you've heard of any other buzzwords like proof of stake or sharded proof of stake or like delegated proof of stake or proof of space-time or whatever like other buzzword, basically any blockchain can be broken down into 5 layers. And those 5 layers are storage, networking, how they create their accounts and how transactions are created and what that even means, mining, and then verification. So if you think about like Ethereum, for instance, how they do transactions are different than Bitcoin, for instance. Ethereum has transactions that relate to smart contracts, and accounts are also different. Accounts can be an account for a human, or account can be an account for a smart contract. So this is kind of like one example of how like, even though a blockchain might seem extremely different, like Ethereum is very different from Bitcoin, they actually have the same layers. It's just that, they maybe like made one of the layers a bit different. Cool. So before I go in, are there any questions? Are we good so far? Questions, concerns, comments?
I mean, one question, I guess I know the answer to it, but I'm wondering if maybe the listeners would be curious, is for full nodes, you were talking about all the negatives and stuff, like about, they require all this work to download all the history and stuff like that. Like why even have full nodes then? And is your approach to like make all that go away when you go in the browser? Is that like, how are you going to do that? Because it seems like if you just move it to the browser, it's still going to you're still going to have to leave your tab open for a bunch of time.
Yeah. I mean, like the storage layer kind of answers your question. So I think there's like 2 questions in there. So one is like, does the blockchain actually need to download all this data? And the answer is kind of like yes and no at the same time. So a lot of times they download the full data for like honestly philosophical reasons, if nothing else. So if you look at Bitcoin, for instance, Bitcoin as like pure blockchain data is roughly 300 gigabytes at this moment. But what you really care about, like when the miner actually starts from like the Genesis block, which is block 0, and then goes to the next block and like process all the transactions, what they really want is like at the end, there's like this global data storage. And for Bitcoin, it's called the UTXO set. And really all that is like, okay, what is this data structure that I can quickly ask, like, how much does Faraz have? Or if Faraz is trying to make this transaction, is this a valid transaction? And that UTXO set for Bitcoin is 3 gigabytes. So you have 300 gigabytes worth of data to come up with a 3 gigabyte data set. And that's really what you want. That's actually what you need in order to like verify transactions. So for us, we actually have a different mechanism where you actually download that global data structure first, or not, maybe not even first, but like you actually like request it from the network directly. And then once you get the data structure, you actually have like a proof that like, hey, like this actually does connect to the Genesis block. And at that point, right now by default, all of our nodes actually do download all the blocks to Genesis block, but at that point it's actually optional. So like, and I'll kind of go into over like how our blockchain works and actually like, we don't, no worries. So yeah, I guess I can go on to the next slide.
Yeah, go for it.
Or actually, I actually wanted to throw in a question really quick before we get too far along. But so I know you ditched Rust, right? Because it was annoying, which is great. I mean, fine, but the whole rationale for picking Rust, if I remember from a couple of slides back, was that it had this cool stuff for zero-knowledge proofs.
Yeah.
So I'm actually really curious, what happened to the zero-knowledge proofs? You got rid of the Rust. Where did the proofs go? Or will you come to this later?
We actually will come to this later.
Okay, then I'm going to wait for it.
Okay, well, to answer your question just like a little bit, and then talk more about it, is we didn't get rid of Rust entirely. We can't for that particular reason. And instead we use WASM. So, and I'll go into like the pros and cons of WASM and like what went wrong or what we did there.
Okay, all right, I will wait for it.
Okay, cool. Yeah, so the first one is storage. And it's kind of like something that Faraz was talking about, like, well, isn't like a full node usually require like a ton of storage? How do you do that in the browser? Do I need to keep my tab open? So first, like, what is storage? So storage is basically how blockchain represents like transactional data and how it saves that like global data structure tree. And if you think of like, okay, well, what like DBs do we have available in the browser? Probably the one that everyone uses that I know of is IndexedDB. And I think it's like probably the most mature database right now. So when we're like trying to figure out our tech stack, we immediately chose IndexedDB for our browser implementation. Unfortunately, Node.js doesn't actually have an implementation of IndexedDB, and instead, uses LevelDB, or like what we chose for Node for the Node part was LevelDB. And then we kind of had a question of like, okay, well, we don't want to make 2 code bases, like one for the web and like one for the Node, because like once we do that, then like one will be like better than the other at some point. We actually want to keep them both like as equal citizens. And so there's actually a pretty great open source library called LevelUp that we're using, which allowed us to kind of have this generic layer of abstraction to kind of like cover both stores. So it kind of looks like this. So basically it's one code base, but like it basically determines, okay, like am I in the web or am I using Node? And depending on that question, it uses 2 different data stores. So this is mostly like for convenience reasons. So then the other question is, okay, well, like, can the browser actually store a lot? And the answer is yes, yes, it can. So Chrome in particular allows the browser to use up to 80% of total disk space, and allows an origin to use up to 60% of total disk space, which is pretty incredible. So like if I have a disk space of like 500 gigabytes, I can use 300 gigabytes for like the Ironfish node, for instance, if I did that math correctly. So it's pretty great. And not only do we have like what we call like optimistic sync, which is kind of like what I was describing earlier. I kind of don't want to focus too much on that because I would go into the weeds of like how Ironfish works instead of like how we fit in the browser. But also like our annual growth actually won't be that bad. So kind of like pencil math, will be roughly 4 gigabytes a year growth depending on usage. And so the way our blockchain is set up is it does have linear growth. Even our global data structure has linear growth, but it's not by that much. And so, like, can the browser support it? And the answer is like, well, yes, like it actually can. So I'll pause here. Did that sort of answer your question? Yes, no? For us? Oh, I think you're muted.
Yeah, it does. Yeah.
Okay, cool. Great. Okay, cool. So then the next layer is networking. And that's kind of what I was talking about before. We went with WebRTC and WebSockets. WebSockets are still necessary with something called signaling in order for two connections to actually, two nodes to actually make that connection over WebRTC. And so every non-browser node Ironfish is actually also technically a Bootstrap node. And basically what that means is that like when a node first kind of comes online, it kind of needs a list of nodes that it already knows is like, that they are online to connect to, so that those nodes can introduce them to other nodes. So those are called Bootstrap nodes. And those Bootstrap nodes are the non-browser nodes that actually help, like, for instance, like a web browser node to connect to other nodes. So the architecture here is kind of looks like this. So if you have, for instance, one node and it first connects to a Bootstrap node over WebSockets, if that Bootstrap node knows a different Bootstrap node, then you can have a node to Bootstrap node also over WebRTC. So it's kind of like a mix of WebSockets and WebRTC. So this way, for instance, you can have two browser nodes, so like two people on a laptop. With the a facilitation of this Bootstrap node, they can actually form a direct peer-to-peer communication over WebRTC using like this facilitator kind of architecture. And yeah, like every non-browser node, for instance, becomes a Bootstrap node that actually helps the system. So in this way, we don't actually need like dedicated like stun or return servers, because every non-browser node, and actually technically all the browser nodes as well, help with that signaling and basically become stun servers themselves. So yeah, so then to answer the previous question of like, well, did we really get rid of Rust? And the answer is no. So as I was saying earlier, we kind of took these zero-knowledge proofs, which are very like heavy-duty cryptography, definitely in Rust. There actually are JavaScript implementations of ZK Snarks, which is a type of zero-knowledge proof that we actually took. And for anyone interested of like, oh, well, how do I get into zero knowledge proofs like on the weekend, for instance, like can I make a hackathon project? There actually are like a ton of really high quality, in my opinion, open source projects that allow you to like write these proofs in something called a DSL, domain specific language, that's actually all in JavaScript, or actually combination of JavaScript and WASM and Rust as well. But ours in particular was like pure Rust, like very heavy duty. And so we actually, we kept all of that still in Rust and we exposed it via WASM. And so, that was definitely like I thought it was going to be a much easier process than it actually was, but it is very doable. So then what happened when we moved from Rust to WASM? And the biggest hit that we saw was performance. So for us, on using like your I had my 2015 MacBook Pro, for instance, it took roughly like 3 seconds for me to generate a transaction. So when you generate a transaction, it kind of actually runs like all these heavy duty zero knowledge proofs in the background to generate that proof that allows you to make this private transaction. And so it is like pretty computationally heavy, but still like on my 2015 like MacBook Pro, it took like roughly 3 seconds to make a transaction. But now that we actually move things into the browser world, we had to get rid of multicore support. So you can't do threads anymore. And what we realized is that WASM, like even single-threaded Rust, was faster than WASM, primarily because I think, at least in theory, because of SIMD support or SIMD support, however you pronounce it. And so what that means is in Rust actually has like optimizations for if you had like multiple multiplication operations, and it kind of knows ahead of time, like, okay, I have like a lot of multiplication operations to do. There's like additional optimization that Rust does kind of natively that WASM doesn't. And so even though like if you like read a bunch of like benchmarks of like WASM in comparison to like native code, I think the stats are something like, okay, well, it's only 10% slower. And for us, we actually saw I think like 2x slower purely because of that. And then kind of the rest was because it didn't have any threads. So, that was kind of a pretty big hit. And so we kind of brainstormed, okay, like, well, how do we make this better? And so if you guys are familiar with this, there actually is something called WASM threads. For pure web world, we don't have threads, but we have web workers. And WASM threads are essentially web workers, but with shared memory. So web workers by themselves, almost like an isolated environment that runs in a different thread. And then maybe it comes back, and the communication to and from the web worker can be sometimes expensive because you need to serialize and deserialize data. And so shared memory would like very much help with that, because then all of a sudden you can have like threads in kind of like the same logical kind of headspace as you would in like a native language. So we looked into like WASM threads of like, okay, can we use WASM threads? I think like as of Chrome 74, 75, they are now by default in Chrome, which is great. They're not in Safari, and I don't believe they're in iOS Kit as well. And so we kind of felt, okay, like WASM threads are still pretty experimental, and they're not actually as easy to work with in Rust as you would imagine. And so we kind of like left that in the back burner, like, okay, well, maybe like get back to it later if it's like more established. And then we thought of, okay, well, can we use the GPU instead? There is something called like WebGPU, but unfortunately, it's like even further behind than the WASM threads. And if anybody like has more information of like the status like WebGPU or like WASM threads, like please let us know. Like I do want to keep track of these things because it can like very much impact our project to make it faster. So then the fourth layer is mining. So a full node basically has to mine. So as I was saying earlier, like for other chains like proof of stake, they still have the concept of mining. It's just that it happens differently. You have like a different election for how you become like that particular node that is elected to produce a block. So for proof of stake, it's you have to stake some money to be like as part of that consortium to be like to be chosen to be a block producer. For proof of work, you have to like hash this algorithm, and the first person that gets a hash that's below a certain threshold, gets to produce a block. So there are tons and tons of algorithms for proof of work. And the history behind proof of work is like when like Bitcoin and Ethereum became like more popular, we started to see a lot of ASICs, and ASICs are specialized hardware that is specifically built to like hash that particular algorithm very, very well. And so the evolution of hashing algorithms is that people started to make them memory hard in order to make them ASIC resistant. So memory hard just means that, okay, in order for me to hash, I need to have like a huge data set. I need to choose like some random number from this huge data set, and this huge data set requires me to like, say, keep like 2 gigabytes of RAM in memory, like as I'm like searching for that particular like part of that data set to use in my hashing algorithm. So what we went with is a mining algorithm that can be done in browser. We actually haven't chosen one yet, but we're definitely picking out of the ones that can be easily done in browser. And the thought process there is, yes, that if you are going to be mining in browser, you're not going to be as performant as the desktop version, purely because like you can have threads on desktop. Can't really have threads in the browser. I mean, you can have web workers and stuff, but it's not the same. But still, like the idea is that like, once again, we want to fit we want to fit this full node into the browser, and you can't really, call yourself a full node without mining, sort of. Cool. Should I pause for questions here? Oh, you're still muted.
Sorry about that. I think Makola's having some connection issues, so he just dropped out. Hopefully he'll
should I wait?
In a second. No, it's all good. No, we should keep going. But no, I think it's I hadn't realized all the parts that were going to be necessary to like put a full node in the browser. I'm really glad that you're like going through all the like actual like nitty gritty. It's like really a stress test of the browser and its APIs. Can it actually allocate as much memory as you need? Can it actually do threads? Can it do SIMD? It's I bet you've learned a lot about all the different nitty gritty. So I guess I don't have a question. I was just that's what I was thinking. That's what I was thinking while you were explaining this. I was like, I hadn't realized that you need all these things. So
yeah, for sure. I feel like we're pushing like all the boundaries. We're like, okay, can we use WASM threads? Maybe not. Can we use WebGPU? Probably not. Like, like when is like SIMD coming to WASM? Like, I think in one of our like linear tickets, I have their GitHub issue, like, linked there. It's like, okay, pay attention to this, because like once SIMD happens, like, so all of a sudden we're gonna have like 2x performance. So yeah, like I didn't realize like we're gonna be hitting like literally all the bounds of the browser in order to make this happen. Yeah, but it's happening for
Nice.
better or worse. Cool. And then I think the last layer is verification and consensus. So consensus is kind of like a fancy word for what are the list of rules that a node needs to follow in order to accept transactions or blocks. That's it. Sometimes there's a consensus layer, like, or consensus rules for like the network, but those are rare. Well, maybe not rare. Anyway, so for us, like verification, like what is verification? Like, okay, like is this transaction valid? Is this block valid? So a lot of those checks can be done purely in TypeScript. They're pretty cheap to do. For the transactions in particular, because we have these zero-knowledge proofs, we do need WASM support to even verify the zero-knowledge proofs. But once again, like we kind of already went through that pain. So the verification consensus layer was actually like pretty simple to implement. So to kind of go over all the layers, storage. Storage can be completely done in the web browser. IndexedDB allows you to have, or I guess Chrome allows you to have like 60% of your disk be accessible via the web browser. And like if you have fully synced your Ironfish node, and you close the tab, that data doesn't go away. Like it's actually stored on disk. So like if you open it back up, like if the data is not gone, you don't need to like re-download everything from scratch. Networking. So networking, we switched to WebRTC, and we actually got the like pretty easy peer-to-peer connections kind of for free using WebRTC. And kind of one other note for that, for Bitcoin, like one thing that was kind of surprising to me, especially when we started to doing more of this research, is like when you think of Bitcoin, you think like, wow, like Bitcoin must be such a huge network. Like I see it in the news, I hear about it all the time, I like see the price go up. And when you actually look at how many full active listening nodes there are supporting the Bitcoin network, the number is around 10,000. And to me, that was really surprising because I expected that number to be like a lot larger. Like I used to work at Airbnb, and we have some people on our team who like used to work at Facebook, and like like for Facebook, like 10,000 servers is like one feature. Like it's it's kind of a small number when you kind of think about that. And there are many reasons for why there are so few Bitcoin nodes. Like once again, it requires like a lot of resources from your laptop, but even then, like not that much. Like 300 gigabytes is like not that much. So my theory is that it's purely because people don't want to go into their like router configurations or like their firewall configurations and like set up port forwarding to actually make that pure peer-to-peer connection. So it's really cool to see how with WebRTC you kind of like almost get that for free and actually get to like a peer-to-peer communication a lot faster. Anyway, so the account and transaction creation, for us, this is still primarily in Rust, and we have like a WASM glue layer that allows us to kind of use this in the web. Mining can also be done purely in Rust. Usually, actually, like if you're successful, then other people will write custom miners for your node. So basically, they kind of use your node to kind of get new pending transactions, so a miner can actually make a new block. And then give it back to the node so it can propagate it to the system. So the mining here for us, for instance, is like purely for like testing purposes for us because we know like other people write kind of miners for us. And then the fifth layer is verification consensus, which for us is a combination of TypeScript and WASM because we chose TypeScript across the board as like our main JavaScript tool of choice. Yeah. So yeah, it's kind of as I was saying before. What's cool about WebRTC, and I kind of had a snapshot of what it looks like when you start an Ironfish node. This actually happened today from Jason, a coworker who lives in San Francisco, but definitely we're working remotely, and he was just able to send me his like connection. I was able to connect to it, and it was kind of a magical moment of like, oh look, I don't have to go into my router settings. Like it just works. So that was pretty cool to see. Cool. So then for people who are interested in like, okay, well, when can I use Ironfish? When is it in the browser? The answer is hopefully soon. So we are trying to launch our CLI implementation first. So I know that CLI is like not as exciting as the web browser itself, but our entire tech stack is built so that we can actually fit in the browser quickly afterwards. And so it'll be CLI first and then browser implementation next. Cool. And I think that's it. So now it's all for questions.
Amazing. Wow. Well, thanks for that. Really cool talk. Yeah, so we have some questions in the chat, and I had a bunch of things that came to mind. But first, I just wanted to say, like, I was having flashbacks of working on WebTorrent from all the just all the pieces, you know, coming together and then having it that moment when it works. That's really magical feeling. And also liked hearing your explanation of the thought process, because you know, when you're doing stuff like when you're working on a project like this kind of cutting edge and you're using so many things, it's like really a challenge, like, you know, because the browser is almost like not meant for an app like that, or for a use case like this. You know, the like specifications are optimized for client server a lot of the time, and you're really trying to have like so much logic in the client, and you're not really involving a server. You know, you're trying to do browser to browser, and, you know, maybe browser to yeah. So it's really pushing the limits of like what the browser can do. And so this mad like dash for like, oh, can we use like web GPU for this, or, oh, is that ready, or does that work in the browser? Totally relate to it.
Yeah. Oh, sorry, go ahead.
No, go ahead. You go ahead.
I was going to say, like, I'll challenge you, like, why isn't the browser built for this? Like, when we started this project, like, why did we even start this project? There actually are other privacy coins out in the market. So our privacy mechanism is, at this point, very, very similar to Zcash. And it's already, like, out and about. And Monero is another one. And so we started this project because we wanted to make a privacy coin that works and is usable. And for Zcash, for instance, it's really hard to use it in its private form. And like Bitcoin is too, and Ethereum is too, if you wanted to like run a full node. And so for us, it's like, well, like, you know, we're seeing so many tools move into the browser. Like, you know, we had like Word, and now we have Google Docs. We had like, you know, like Adobe products, now we have Figma, right? We're seeing like such a shift of these products being used in the browser, because the browser is how you get usability and how you get like collaboration. Like, how do you get like you know, cross-platform, for instance, accessibility. And so for us, it was like, okay, like, if we're going to be building like this blockchain for everyone, then it has to work in the browser, because, you know, everyone who has a device probably has access to a browser. Now, it's not going to work on all devices, but but it'll be pretty close, right? So like, if you can run like Chrome on your device, and chances are you can probably run the Ironfish node on your device as well. So that was like really like the motivation there. And so like, yeah, like maybe the web browser isn't entirely built for this, but, you know, like we're using like web workers, WASM, and TypeScript, and WebRTC, I guess, and all these are pretty established now. So I don't know. I feel like the browser is definitely getting there.
Yeah, totally agree. Yeah. I'm like very pro browser and pro like doing as much using web tech as possible, for sure. But it does seem like you know, you mentioned like the SIMD and the thread problems, and the transactions taking 45 seconds and that kind of thing. Is that stuff just all going to be fixed like in a year or whatever, however long it takes, once WASM can do SIMD and can do threads, and once that like makes it into all the browsers, is there a path to like making it like really usable in the way that you want, or like what are the other roadblocks besides the ones I just mentioned?
Yeah, I mean, those are basically all the roadblocks that we have so far. But we like, for short-term gains, like, okay, well, is there something else that we can do? And we are looking into like several solutions. So right now, like, our transactions take like 45, 50 seconds to work in the browser. And the reason for that is because like, well, the computation is actually pretty hefty. So is there anything we do there? And so we're actually looking to like replace our hash function. You know, and like, that's a much more riskier thing that we may or may not do. This kind of gets into the weeds of like how zero-knowledge proofs work. But for zero-knowledge proofs, there are something called like a Snark-friendly hash functions. So like hash functions that are built specifically to run more performantly for zero-knowledge proofs. And there's one that came out like in 2019 called Poseidon hashes that actually give you 8x improvement in your ZK Snarks. and use zero-knowledge proofs. So we're actually looking to change our hash function that'll give us 8x gain without like SIMD or without WASM threads. So like that's like something that we're looking at. That is a pretty aggressive change because like there's a reason why not that many people have used this particular hash function, and the reason why is because it just came out. It actually has been peer reviewed, it has been audited, so it seems like very, very safe. But if you like know any cryptographer, they're like very cautious people, and so everyone's kind of like waiting, like okay, like if 20 years have passed and like this hash function is still not broken, it's probably good to go. So like we're looking into that. But I mean, yeah, going back to your question, like short-term gain, like if we can figure out how to use like WASM threads, if we like say, okay, like we don't care about Safari or iOS Kit, like maybe we can just use them, like maybe that'll like help us too. But yeah, SIMD will give us like 2x improvements. So like I'm pretty excited for that because that's like no work from us.
Right. Makola, do you have any questions? Oh, I think let me unmute you. Okay, go ahead.
Okay, I can talk again. I sorry about that again. I actually dropped in the middle of the thing, and it was actually because my router messed up. So go figure. I had to turn it off and turn it back on again.
Those routers ruining everything.
It's terrible, right? Why do we even have these things? Why can't I just connect to the internet? I don't know. But I actually have a question about the WebRTC stuff. So. And maybe you went over this in the talk, but about how many peers do each of these nodes need to connect to in order to work?
Ooh. Yeah, great question. So it really depends. I think the browser, there's a limit. I think the limit is 256. But to kind of give you a comparison to like other blockchain implementations, so Bitcoin actually, I think they hard-coded it, or they strongly recommend, plus they hard-coded it, of 8 nodes. So if you're a Bitcoin node, you connect to 8 peers, which once again, to me, sounds like, wow, that's very little. Yeah. You ever use WebTorrent? Not that anyone would. You definitely have a lot more peers trying to download a file.
Yeah, we actually oversaturate the network with connections. We like do like 60 per torrent or something crazy like that.
Okay,
definitely
yeah.
not that many. Yeah, that's really interesting. 8 nodes in Bitcoin. Wow.
Mm-hmm.
So
you can change the setting by default.
Are you also doing 8 then, or are you doing a different number?
We're doing something more than that. I think, like I said, I think the limit is 256. I think like right now we have set the max limit to be 256. And then once we get a testnet up and we can actually have like that many connections, and if we see that there's something wrong with that many, we'll tweak that number to be something lower. But yeah, I think essentially, if I'm not mistaken, and I might be mistaken, it's 256 for the entire browser or for origin. But that's kind of okay. Okay, cool. But yeah, around that.
Yeah, and then for the client, would this run in like a page, or would it be like a service worker or something like that? Because like, again, there's like a long startup time with it, and then establishing all those connections and getting like plugged into the network probably takes a while. So
yeah. So what we actually learned the hard way, unfortunately, is that you can't have your networking layer run from a web worker. And so our entire node kind of runs in the web worker, and then the networking layer is outside that. And then we have like a network bridge that kind of like mitigates, like, sends those messages across. But yeah, to your point, yeah, like the entire node is technically in a web worker, so it doesn't like freeze the main thread. That would be like a pretty terrible user experience.
I think service workers, they have like a life cycle that can live like beyond your tab. Like you can close your tab and then the service worker can still run in the background. And I know they can make like HTTP requests, but I have no idea if they can do WebRTC or not, because it's been a while since I've looked at it.
They can't.
Okay, then never mind. Terrible.
No, it's terrible. Yeah, I actually I opened an issue about this a long time ago on the working group like GitHub, and I was like, please add WebRTC to workers. Because WebSockets work in workers, and so at least I think a WebRTC data channel is like pretty analogous to a WebSocket, it doesn't seem to me like there's any reason why you wouldn't want to allow that in a worker, but I think it's just for whatever reason not high enough priority that they've gotten to it yet. But anyway, Elena, it sounds like you have another use case. Maybe you could chip in on that issue and try to make.
Okay.
Yeah, I think like so many people really would love to have like a data channel only WebRTC, but it's so hard to like find that, right? I mean, at least last time I looked at it, which was a couple of years ago, it's like every WebRTC implementation comes with all this other stuff, right? That you probably don't even want, like these video and audio things, which are good. We're using them now, but.
No, there is actually there are a couple of implementations that just do data channel that are like written in C or C++ these days. In particular, there's one called, I think, like it's lib data channel, and the reason I know this is because somebody just this year sent a pull request to libtorrent, which is the like one of the most popular C++ implementations of BitTorrent. And they added support for WebTorrent, and in order to do that, they needed to integrate a WebRTC library into this like C++ code base. And to your point, Mikola, like a lot of the main WebRTC implementation and a lot of the other implementations that other people have tried to make have all this video and like real-time video and audio processing kind of junk that's in there that you don't need for something like what Elena's building or for something like WebTorrent. And so what you really want is just the data channel components. And somebody finally like went and made a really good implementation of that. And so that finally is what enabled like this C++ project to be, you know, this relatively lightweight C++ project to be comfortable like embedding an entire like WebRTC, the data channel stack into the code base, because it didn't blow it up in the same way that like embedding the whole libWebRTC from Google would have blown it up.
Yeah. Or what was it, like libjingle or compiling that thing, or I forget what they used to call it. Yeah, that horrible thing. Yeah.
Totally. Yeah. So yeah, I think it's like possible to do it, but there's still a lot of layers in the stack that make it seem like a little bit kind of complicated. But I think I don't know if you've looked into web transport, Elena. Do you have any thoughts on that? Because that seems like maybe. You can't really do browser to browser or true peer-to-peer with it yet, I think, but I don't know if it's helpful at all for anything that you're doing or if you've looked at it.
No, I don't think we actually even looked at it. So yeah, like, can you tell me more about it?
I think, so my understanding of why you would ever use it is that it's sort of, it gives you the ability to have unreliable kind of quick type
I see.
Connections without needing to use WebRTC on the server side, which is like still like a pretty heavyweight thing that doesn't scale very well. So it's a much lighter weight thing to run on the server, and then you get like basically UDP access. That's kind of the main use case that I've seen for it, but I honestly haven't looked into it that much either. Gotcha.
Should we answer some of these questions?
Yeah. There's so many good questions in the chat. I agree. Yeah, we've been ignoring them. I saw one that I wanted to ask from Alex when we were talking about all the connections and like how many you open. Like he was wondering if normal like consumer off-the-shelf routers get bogged down with like the number of peer connections, that you're creating.
I don't actually know, but I think like you would know, right? With WebTorrent, like how true is this for WebTorrent?
I mean, if you create hundreds, then yeah, you can crash consumer routers. That's been my experience. Hundreds can definitely do it. Okay, that seems reasonable. Like how many? Like upper hundreds? Just so I know. I mean, I think I don't remember. It's been a while since I like worked on that part of the code base, to be honest with you. So I don't know off the top of my head. Okay. I thought maybe you would have like more recently played around with that, but I guess you're not creating that many WebRTC connections anyway. You said like so. No, it's just like us. We're a 6-person team, so we're a 6-person team now as of yesterday, actually. So, yeah, but yeah, once we start. Sorry, go ahead. Oh no. Should we choose a different? Any other questions stand out to you, Mikola or Elena?
I'm a little bit curious about the ZK Snark stuff, or the particular systems you used. I kind of missed that part. Could you say again which code you used for implementing them, or did you roll your own like Snark thing, or how did that work?
No, I mean, so if people are familiar with like the ZKP world, so there's different types of zero knowledge proofs. We were using the ones called ZK Snarks. And so for ZK Snarks, there actually are a ton at this point, like implementations. We're using a pure Rust implementation called Bellman, which is kind of like lets you write your own circuits. This kind of gets into the weed of how zero-knowledge proofs work. But for people who like actually want to, use these like on a weekend or like tomorrow or like today even, there's a ton of like much more accessible libraries out there. So there's actually one called Circum, and from a company called ident3, something called Snark JS, which is kind of a compatible library. And it actually allows you to use what's called like a DSL, domain specific language, to like write your own like zero knowledge proof app. And it's all purely like in JavaScript, and it like, runs in the browser by default. So yeah, there's a ton of like implementations. We took like the super heavy duty Rust implementation one, and we actually still kept it. So we actually have that running with Wasm.
So like as a ballpark, how big are the circuits go into to like run this?
Yeah, so it depends on how complex your proof is. So there was actually a game that, like a zero knowledge proof game that recently came out. It's called Dark Forest. And, like it's from like, once again, like works in the browser. So you can like generate these proofs in the browser, and they take like, like a fraction of a second. And that's because the proofs are just so tiny. Like, I don't know exactly how big the proofs are, but they're super tiny. And then, oh yeah, there you go. And then for us, the proofs are a bit bigger. So, like when I was like playing around, like I think like if you do like a Sudoku game, you might get a couple hundred what's called gates, and gates correspond to how big your proof is. And we're like on a magnitude of a couple 100,000. So that's kind of how it is. And then yeah, like for like you do have like verification keys, and those can get kind of large. But for us, like our entire Wasm library is about 50 megabytes, and we're trying to like really like, I think we can get down to like 40 megabytes, which I know isn't like super great, but but yeah, that's kind of how big the project is.
Are there like easy ways to do like recursive circuits so you can like run them in a loop or something? Maybe optimize it like that, or I don't know. Maybe that's just a dumb idea. Yeah,
so it kind of depends on how your zero knowledge proof works. So there are certain zero knowledge proofs that can run in parallel. This one in particular, there's a ton of things that have to be done like in serial, and so unfortunately, even the multi-core component actually does speed it up quite a bit. But yeah, like that's pretty much like the limit for how fast. Like more cores is not going to help you that much at some point.
Yeah, but like if you have like a hash thing, you could replace like a fully expanded circuit with like a loop, right? And then you only have to like have the loop part of the circuit, and then you could maybe do some kind of tweaky optimization stuff like that. I don't know. I haven't actually like played too much with like the Rust ZK Snark stuff. It's on my to-do list, but I just don't have the time to get into it. But it's like it's pretty high up on my to-do list. It's probably like one of the things I'm going to look at soon. So I'm just kind of trying to pick your brain to figure out what works and what doesn't work, so don't waste too much time.
No, I mean, yeah, it's like, so Bellman is the Rust kind of implementation for ZK Snarks, and it is not a domain-specific language. So you kind of like manually kind of write your circuits, even though it has like a lot of gadgets, a lot of helper libraries. It's not like you're purely writing circuits by hand. But it like there are like Circum, for instance, is one of them that have like domain-specific language like on top of it. And there's many others. If you like want to connect, we can talk about it more offline. But Circum is like one that I recommend, and that's like way easier to get into like the ZKP world, because instead of like writing your own circuits, which actually does get into like the weeds of how these zero-knowledge proofs work, you kind of have this like domain-specific language. You can write like pseudocode that helps you like write your zero-knowledge proofs, and that's actually what Dark Forest is built on. It's using Circum. Yeah.
Okay, cool. All right, well, I'll take a look at it. Those are some good references.
I have some questions that came to mind during the talk that I guess I can ask now. I was wondering if so one of the I guess issues that I would worry about with the storage. You mentioned you could use like up to 60% of the disk. Is that like liable to get like evicted by Chrome if they realize that like other apps on the computer are using up that disk space and they need to get it back? And if so, like, does that, it just means you have to re-download it again later or something, right?
Yeah, I mean, I found some Stack Overflow issues where people are talking about like when do things get evicted. and it wasn't super clear to me. So we haven't ran into this issue yet. So we might eventually, but it seems to be okay for now. And also, once again, like we're not using up to 60% of your storage. Like we actually need a lot less. So yeah, our growth is like 4 gigabytes a year, which is like pretty reasonable. So like even in 2 years, it should be like, I don't know, 10 gigabytes at most.
Yeah,
right.
One thing is you will probably run into some issues if you try to do this in mobile Safari, where the storage limits are significantly stricter than they are.
I'm sure.
Yeah, like I think it's actually only a couple of megabytes. You barely get any at all to like, work with local storage. So it like might as well not even exist on iOS.
Okay. Darn. Yeah.
Sorry,
for mobile, for mobile, we have like a different strategy, but like it was always like in the back of our minds, are like, oh, how cool would it be to like run a full node like on your phone in the browser?
I think if you manage to somehow get people to hit the add to home screen button, which is really hard to do because very few people will actually do it, then you can like promote yourself into a PWA, and a lot of those limits get relaxed. But it's so hard to trick people to like hit that button because it's like no one will do it.
Gotcha.
You can kind of walk them through it with a GIF or something maybe and help them.
It's not easy though. The consumer habits aren't there. The only way people know to get a thing on their home screen is to go to the App Store and then install it through the App Store. They won't do it from a web page.
I mean, it's still cool though that like, I mean, so I think that really like the fact that you can run it in a browser on like the open web is it just lets you, it just gives you an additional option. You know, in terms of how to interact with the Ironfish network. It seems like, you know, you can always just make native apps too if you need to. In fact, I mean, like one question I wanted to ask about is kind of related to that, is say I'm really paranoid and I like don't want to trust that every day when I go to like access my wallet that you're going to serve me the correct JavaScript that hasn't been like messed with either intentionally or accidentally or whatever. Like it seems like for those people, for some segment of your users, they would just want to just get like a native app that they would install. And it doesn't seem like that your decision to do it all with these web technologies precludes you from making a native app. Right? Yeah.
Yeah. So even like, you know, the first version that we're going to be shipping is going to be like the CLI version. And so, yeah, like for people who don't trust like web, or kind of like what you said, like maybe they have some reservations, you know, you can generate your keys like offline using the CLIs, like all that still is like available for you.
Right. Yeah, but by deciding to do WebRTC, you at least allow the option for these web full nodes to be a thing. Whereas if you had chosen something like TCP or whatever, it's like, okay, never going to happen, not possible on the web.
I mean, so TCP kind of, maybe not on the web, but I mean, like you can do like all like hole punching and all that like with TCP as well. People have done it. It's just like a lot harder.
But like a random web page can't like open a socket, right? Yeah. That's interesting. So then I guess one other thing that I think about when I think about the tabs, this is a criticism that people also had of WebTorrent a lot, was that like, well, these are going to be really poor peers if you have all these like tabs that are just running for like 10 minutes or whatever. Are they really going to be making a contribution to the network? Or are they just going to be mainly leeching and then just like disappearing? And so basically a net negative to the network. And that's like one of the things we got a lot of like questions about. I don't know if you have thoughts on that.
Yeah, so we actually had a pretty big internal discussion around WebRTC and WebSockets, and the discussion was, should we, like when you make that like initial like connection with the WebSocket, do you immediately upgrade yourself to WebRTC so that the network isn't like split into like purely WebSockets? Because you can kind of assume like, okay, if I'm using a WebSocket, that means I'm a non-browser node, and like, will there be discrimination against browser nodes? So we actually had a discussion of like, can we mask it by forcing everyone to use WebRTC? And then we kind of realized, okay, maybe like we're over-engineering this. Maybe we should like not do this until we see this as a problem. But yeah, like I'm kind of curious your thoughts. Like if a node can or make some assumptions based on the connection type of whether or not a node is a browser node or a non-browser node, would they discriminate against that node?
Yeah, I don't know. That's a good question. I mean, in the case of WebTorrent, what ended up what was the criticism was that like as an implementer of a native torrent app, what would be the incentive for them to support talking to web nodes? Like, would their users ever demand that, or would their users ever care or like want to be sharing with these web nodes? Because mostly, if they're just leeching, that was the criticism. But I mean, in the case of torrents, it didn't really make sense because like most people's internet connections have just gotten so much faster in recent time that like you end up getting the whole like file that you're downloading in like a matter of minutes usually, even for multi files. And so the rest of the time that you're consuming it in WebTorrent, if you're consuming it using like streaming it out of the torrent or something like that, you're actually seeding it that entire time. And so even if if you're only there for a couple hours, that's still mostly time that you're seeding. And then the other thing too is a lot of peers are, these people running the native apps are actually doing it out of like an altruistic desire to basically spend most of their time seeding and just sharing. And when you're in that seeding mode, you're really not doing the whole tit for tat thing where you only share with people who are sharing with you. You're just purely altruistically, because you already have the full file. You're just basically altruistically sharing with anyone who shows up. And so for those people, like, I don't see a reason why they wouldn't want to share to browser nodes. And so, yeah, and in the case of WebTorrent, it didn't really end up being a problem.
Okay. Yeah, for us, I don't think it's a problem either, because even though you're a browser node, you're still providing value. Like, it's still like a bidirectional connection. So if you have something that the browser node, or sorry, if you don't have something and browser node does have it, you can still request it from them. So yeah, there kind of honestly shouldn't actually be like any reason why you would discriminate against a web node.
So what about like the discovery of peers? How is that handled? Like, is there something like a DHT, or how do you find who to talk to?
Yeah, so like most, like I can tell you how like other people have solved it, and like we kind of discovered that there's no good way. There's just like some ways that are less bad. But yeah, you need like a list of Bootstrap nodes. You need like a list of, okay, what are the nodes that I know that are actually like are going to be online when my node's trying to be online. And like once you connect to even one Bootstrap node, that Bootstrap node will like introduce you to other nodes. So you just need like one initial connection, then you're pretty much good to go. And so like other people have done it through like DNS lists. It's like that's kind of like what Bitcoin does. And for us, like it's okay. Like, well, for now, we'll just give you like a config file, and you can like we'll have defaults for like here are the Bootstrap nodes that we know of. Then any user can just like go in and like change in their config file. But yeah, I mean, like people are solving basically this problem the exact same way, just like with slightly different methods. Yeah. At the end of the day, it's just like a list of Bootstrap nodes somewhere.
Mm-hmm. Right. It's really interesting. Well, yeah, I guess I think, do we have any other questions from the chat that we want to ask before we wrap things up? Someone said, have you tried running it inside of Cordova or PhoneGap to, I guess, to get it to run on like mobile devices? Maybe that's a little premature though for you at this stage.
Not yet.
Okay, yeah. And then someone else was saying, I guess a few browsers sleep tabs, which, oh yeah, so this is from Alex. He's saying that browsers will sleep tabs which are not in focus. They'll, I guess, stop running timers. And I've actually run into that also before.
I have some thoughts on how to mitigate that. I've had to deal with this problem as well. But anyway.
How did you solve this problem? No,
there's a way. There are ways you can get around
What are the ways?
I don't want to say too much about them, or else Google's going to probably fix it, right? But there are ways you can get around this. I mean, so one of them is like, okay, WebSocket events will wake up a browser. So if you're already connected with the WebSocket to some server, you can just send them like a ping or a heartbeat packet or whatever, and that will cause them to like wake up and do some stuff with that WebSocket packet. So like you can do some things like that to do that, but you basically just have to generate events that will make the tab wake up in some way.
Gotcha.
Okay. Yeah. I don't know. I'm sorry. If you have other ideas, I'm open to them too, right?
No,
I've heard of people running, playing like silent audio files in the background. And
that'll work too, yeah.
Oh, that's a good trick.
Yeah. And I don't know, I think I've heard, well, also I think a thing I ran into was you can just stop using set timeout. You can use, instead you can use, what was it? I'm trying to remember what it was. Oh, I was trying to do process.nextTick, which is like a node thing. And then it was, somebody was like, the shim for it was implemented using set timeout, which is throttled by the browser. And so what you can use instead is this other thing called Q microtask.
Q microtask, yeah, the promise. Yeah. Or you can also do promise.resolve, which is the same thing.
Yeah, exactly. And then if you do that, then it'll not get throttled because it'll just run on the next tick no matter what. But that's kind of, that's a different thing.
But that's not the same thing though, right?
Yeah.
If you have like a task and it needs to run at regular intervals, then there's not that many things that you have that can do it. But you just have to find something that will basically schedule an event that does not use set interval or set timeout, because those up. So pretty much anything that can generate an event. Audio can do it, because web audio is extremely filled with glitches. If you want to find cool bugs, that's the best API to look at, right? Because it's the worst designed web API.
Gosh.
Right?
Okay, good to know. So play a silent song, or not, maybe not even a silent song. That'd be annoying.
Yeah, or you can just use WebSocket. Just send a WebSocket to the client at regular intervals. That'll work.
Yeah.
That's totally reasonable.
Okay.
Right? And I think that's even fair because you're doing some work and the client's doing some work. It's like a mutual exchange, you know? They shouldn't even fix that one. It's fine.
Yeah. Cool. Those are good tidbits.
Cool. Well, yeah, I don't think we have any more questions from the chat. I'm good. Nicole, do you have anything to add before we go into the social part?
Nope. Sounds good.
Cool. All right. Well, Elena, it was great having you. I loved hearing the journey story, and especially all the different false starts and different things you tried. Super interesting. And we're grateful that you came to share that with us. Yeah, and of course, welcome back anytime to come and share progress on your mad science and anything especially to do with getting stuff to run in the browser. It's always interesting. And then I just wanted to mention one other thing. Next week we're going to be doing a talk by John Heisey, who's spoken once before, and he's going to be talking about restoring his 1960s color television, which has nothing to do with JavaScript, but it is a really wild project that he's been working on for like over a year. And so it's mad science, it's just not JavaScript. So if you're interested in old like video technology, kind of along the lines of Substack's talk, which was, if y'all remember that, that was from a few weeks ago when Substack was sharing how he did, how he sort of was reverse engineering VHS and NTSC and a bunch of cool stuff like that.